All right. Next up, we have Michael Leibman. He's going to be talking about profiling, stack traces, debugging, performance, something like that. Right.
Thanks. All right. So, hi, I'm Michael. I am also working on the Cloud Console team with Jen. Guess I've been at Google for almost 7 years now, worked on different things, mostly Google Contacts. I was a tech lead of the previous 2 versions, and have started working on the Google Cloud console and the whole platform fairly recently. If you ever used SlickGrid, I've also worked on that. Anyway, I know this is mostly in kind of the world's moved on. Things are all about Angular 2, 3, 4, 5 now. But I'm involved in the migration from AngularJS to Angular with the Cloud Console, so I do have to work with AngularJS code a lot. And as Jen mentioned, this is a really large and complex and chatty application with hundreds of developers, with lots of things being lazy loaded, happening at the same time, lots of things running deferred. So I do work on the performance and latency aspects of the Cloud Console. And something I have to do a lot is debug things and profile things and figure out why things are occurring. So a typical problem for me might be I want to put a breakpoint somewhere. Typically, this is like, say, on a data XHR happening, and I want to know what triggers it, how we got there, what the entire flow is, and this should be easy, right? I mean, you go into Chrome DevTools, you set a XHR breakpoint on a URL containing something, you navigate to the page or the tab or the route, and basically you look at the stack trace and profit, yes? Well, no, not so much. Now, before we go on to the next slide, I do have to say that I had to redact a few things here. I originally created this just for internal use at Google. And I haven't been able to find a large and complex enough AngularJS application to really demonstrate this. I'm sure they exist. They just, this was kind of a pet project, really a couple hundred lines of code that I threw together, and I didn't want to create a sample complex application just to showcase this. But needless to say, there are some problems with this approach. You go through this, and you see a lot of surprises. First of all, you'll see different stack traces showing up, at different times, and it's kind of puzzling. But why is it happening? I don't know. It's not deterministic, right? Sometimes these stack traces are seemingly occurring out of nowhere. They have 1 or 2 frames in there, and it's impossible to identify. Sometimes they're just huge, these like 500 frames in a stack trace with multiple asynchronous things happening. So it's impossible to figure out what's going on. But most importantly, they're lying to you. That's right, stack traces are lying to you. But you can do something about that. And that's what I wanted to share. Why is it happening, right? It's happening because of how AngularJS is working. It's mostly because of the digest cycle. Now, hopefully, if you've worked with AngularJS, you do know how that stuff works. But Angular has a lot of mechanisms for deferring work, and typically they're deferred using the digest cycle. A lot of the APIs you might end up calling, like watch, eval-async, apply-async, post-digest, even promises. AngularJS has its own implementation of promises. They're all kind of keyed off of digest cycle. And oftentimes these things are chained. So if you have a chain of asynchronous events, each one is kind of performed in the next digest cycle, or maybe in the same digest cycle, it makes it it makes it impossible to kind of debug if you're not setting up your instrumentation. There's some documentation on the AngularJS side to help go through that. So what can we do about that? We can patch AngularJS. We can patch the deferred execution mechanisms to carry the context, to carry the stack trace. And there are a bunch of them. We can patch all the ones I talked about with the addition of the on. So you can actually see if you were responding to an event that was triggered somewhere or registered somewhere, you can actually trace that back. There are other deferred execution mechanisms. Some include like request animation, frame scheduler. There's probably a bunch more, but they're not as pervasive, so it's not as bad. So how would we do this, right? Can you see this all right? Right. Well, here's a sample of patching apply async, right? We get the prototype of root scope. We store a reference to apply async original implementation. And then we write our own sort of wrapped executor function. It's going to capture the current stack trace recorded from the error.stack. And then it's going to give you a couple of methods that when this gets called, we restore the stack trace that was captured before. And then when you're done executing the original apply async, we basically restore the previous state. And we keep track of the current state in a global variable, in a global scope, or somewhere in a closure, right? So this would, you do this for all of the deferred execution mechanisms, and then you can, whenever you do a breakpoint, you can look at your global variable and actually reconstruct the stack trace from there. That's kind of part of the solution, right? The second part is what you do for asynchronous tasks. Chrome DevTools does this very nicely if you've scheduled an asynchronous task to happen, like an XML HTTP request or set timeout or interval at something. And when the callback gets executed in the stack trace, you can actually see, and this is fairly recent with Chrome 60, I believe, or 61. You can see in the stack trace where the asynchronous break occurred. So you can actually trace where the set timeout was scheduled. Unfortunately, the default error object doesn't preserve that, doesn't expose that. This is coming only in a debugger. But we can use Zone.js to let us capture that. If you don't know what Zone.js is, do look it up. It's very cool. Basically, it's a library that preserves, that patches everything, patches all the asynchronous invocation methods, and lets you preserve the execution context. So here's how you would set that up. We intercept when an asynchronous task gets scheduled, and we capture the stack trace and set that as a property on a task. And then when you invoke the task, we do the same thing, right? We restore the execution context, the stack trace, we run the task, and then we put it back. All right. So time for a demo. Let's see. Now, as I said, I've had a hard time coming up with a sufficiently nasty and complex demo application. And so I'm just going to demo it in the Google Cloud Console. Unfortunately, this means that the stack trace is not going to be very readable, since this is dealing with optimized and obfuscated code. But it might look something like this. If you can see this, I've cut the stack trace, so no, too small. All right, then we'll go with the real version. Okay, so the entire script, including the benchmark to do this, is something like 270 lines of code, so it's pretty small. We do some nice things trying to blacklist certain events so that they don't clog up the stack trace. But let me just execute that, right? In our application, we have it bootstrapped as part of the application itself. But you can inject this. Sorry, you can inject this as a script pretty much in any Angular application, production, running obfuscated code, minimized code, doesn't really matter. And I'll talk about how to work around that shortly. So here's Google Cloud Console, right? This is in my personal account. It's running obfuscated code. Everything is compiled. You do want to bootstrap this script early on, because it's only going to be recording the stuff that's actually happened after you bootstrap it. So nice place to do that at is, I'm going to maximize it. You can just basically look in the minified code for ng defer bootstrap. It's kind of something that happens very early on in the bootstrapping process. And once the injector is ready, that's a good place to put a breakpoint, right? So let's refresh the page. All right, we hit the breakpoint, and I can either do something like import it from, I don't know, from GitHub in this case, or just I can just run it directly like that. And then we keep going. So from this time on, it goes on and captures everything. And once that loads up, let's see. Let's go with the original repro steps. I'm going to put a breakpoint on any URL that contains an activity. So what I want to know is when I click on the activity tab here, what's going to request the activity data? We click on a tab, we hit, oh, that's not the one I'm interested in. That's the one, activity. So if you look at the stack trace, and take this with a grain of salt because it's all obfuscated, minified code, but in an application with unminified sources, this is going to make a lot more sense. This stack trace is not going to tell you much. But if we go to the console and choose the window.trace, it is going to print out a more kind of meaningful thing. Now, when you run this with your application, and it filters out all of the irrelevant stack traces, stack frames based on function names, etc., you're going to see the output a lot smaller and a lot more meaningful. But it's still, we can still go through this. So this kind of allows you to trace the application back from the initialization. You'll see that no, too much. Okay, you'll see that we started loading some JS code, and I can pretty much tell you right now that this is this stack frame is requesting the template from its cache, and we can see that it got executed. It took 200. It received this result. That's the template. The scope was window object, and then 290 milliseconds later, on a promised success, we continued the execution right here. It started rendering, initializing, compiling, linking, and then requested another template. 114 milliseconds later, on a promised success, we continued rendering. Then we continued rendering. Then we registered the watch listener with this expression. When that executed, we loaded another template. When that executed, we registered the route change success event. When that executed, we executed a listener, and so on and so on and so on. And we can actually get back to the to where the actual XML HTTP request was made. Since we're recording everything, we can keep track of a few more things, right? Between some of these, you can see that, well, first of all, we have the latency, right? This is, you can think of this as how long did it take AngularJS to actually get to executing your function. If this is a promise resolution, you can see how long it took. If this is something that involved a digest cycle, and a digest cycle maybe took a long time to get to it, you can see this. You can use this as a proxy for the interactivity of the application. What else can you do? You can this will tell you which watch expressions, which events it reacted to. If this is not the first time your handler was called, for example, the route change success, I had one more call to that before that. And we can keep track of them. You can configure how many calls to keep track of. We can also use the performance timeline, performance API, to capture all of the events, all of the performance-related events that happened in between when the function was scheduled for execution and when it was executed. So here, we can see that we logged a bunch of performance marks. We recorded a bunch of performance resource timings. And we can use that to analyze what's kind of going on in the application, what might be slowing things down. So if you have a chain of asynchronous events doing promise resolution, And for example, you can see that these were the things that were sort of occurring in between, and these were the things that blocked the execution. So maybe you have some network contention, some CPU contention, etc. Right? Now just imagine the stack trace all kind of without the noise, using unobfuscated names and readable. So what do you get out of this? Like I said, less noisy stack traces. You can see which events triggered the action you're interested in. You can see what expressions were parsed and rendered, what templates were rendered. You can see the latency. You can see the number of times the deferred function was executed. This is useful for things like event handlers. For you can track the recent calls. You can see the values. For example, if you're executing a wash expression and you're executing it on every digest cycle, you can see all the arguments to the watcher. You can see the previous value, the current value, the scope. You can access all of that. You can access all of the network calls made between the scheduling and execution, all the performance-related entries, etc. So you can use this for things like critical path analysis. What got in the way of you running this code? There are some gotchas, right? Like I mentioned, Chrome debugger does have broad support for asynchronous stack traces. The error does not. There's actually, well, there's some talk about having it be exposed on the error object, but it's not quite there yet. Zone.js is very cool, but it doesn't have all-inclusive coverage. Things like mutation observers, post-message, on-message. Zone.js doesn't patch those, so you might miss some cross-frame calls and communications. Source maps. So the difficulty I had in presenting this is the code is optimized, minified, and even if source maps are available, the error object doesn't quite let us access that. Fortunately, we can work around that. There is this very cool project, stacktrace.js, and that includes parsing source maps. So when we print out the stack trace from the tracer here, we can actually use stacktrace.js and parse their source maps and get unminified names. I haven't gotten to that yet, but if you want to pick that up as a kind of follow-up on this, that'd be a great thing to do. And yeah, unminified AngularJS sources work best for now. I've shown you how to use it. I've included the tracer file. It's posted on my GitHub page. You can run it kind of in a similar way I shown you now, or you can integrate it in the application itself. And then from there, you can just access it using window.trace, and that'll print out the stack trace. This is literally, just a small script I threw together to help me debug things. So it's not very polished yet, but if you want to take it further, you can integrate it with stacktrace.js to handle source maps. If the application doesn't use Zone.js, you can just auto-inject that as well. And Zone.js also does something really cool. It does its own handling of the error object stack traces, and it kind of generates a few nested fake exceptions, and then uses the stack traces from there to identify which frames it needs to blacklist. So we can do something like that. For the time being, I'm just filtering things by known names from the AngularJS framework and Zone.js itself. You could also productionize it, turn it into a Chrome extension so that it injects things automatically at the right time. Could do this also using dev panels. I did include a benchmark in there. There's about 7 milliseconds of overhead per 1,000 calls traced with this. So technically, you could include this in your production application and integrate this in your error reporting. Yeah, and that's kind of it. Any questions? Yeah.
Do you have any good ways of taming the Zone.js error output? Like, so when you're running a hybrid application and some error happens with it, blows up, huge, 500-line thing, like just the initial output, like taming that.
Yeah. Yeah, so I'll repeat the question for the sake of recording. The question is how to tame the Zone.js stack traces or I'm assuming you're referring to the Chrome debugger itself, or the debugger itself, right? Zone.js does this for you, kind of, right? It includes the long stack trace as part of it. So what I was describing about the way it discovers which frames to blacklist is it does that, but it can't tell Chrome to ignore them. So if you print out the stack trace using the error.stack, right, or toString itself in the exception, your Zone.js is actually going to filter all of those frames out for you. Anything else? All right. Well, thank you very much.